Bismillahirrahmanirrahim. Welcome to Easy Learn, and this is network analysis. Before going to start, let us first discuss what we already discussed in the previous section. In the last episode, we were discussing about the Kirchhoff's law. These Kirchhoff's laws are the base of networking, and I first suggest if you have not even practiced Kirchhoff laws, you need to practice a lot, because whenever we are ready to apply Kirchhoff law, want to analyze any network, either it is a capacitive, inductive, or any type of network, we first need to write the equations. Then we need to understand the and replace the voltage, either it is a capacitive, then we have the formulas for the capacitors, and if we have inductor, then we have also put the voltage relationship for the inductor. This is the second step, but first we need Kirchhoff laws. So there are the two laws basically we discussed in the previous episode, and I also give you some stuff for practice. I hope you practice that stuff that I provided you in the last slides. And today's discussion is basically based on the equations number, how many equation exactly we need and how we write. So there are the two basic things that we are interested in today's lecture, and we will try to sort out first. But before going towards the today's lecture, I just wanted to show you about my one important thing, very important actually. There is a difference between the branches. Actually, we discussed the branches in the previous discussion, but unfortunately I forget about to tell you in details about one important thing, and that is chords. Actually, so we need to define a relationship and a difference for the chords. Let's suppose this is a first point and this is another point. We also name these points for better understanding. This is our point A, this is our point B, and we have another point, and this is our point C. And if we have another point here, let's suppose this is our D, and this is how we connect the points. We can also connect these 2 points also. So this is a way A is connected with B, C, and D, and B is also connected with all of them. So this is a unique and a prescribed way to explain the different points and different so these are the lines, are the branches. That is, for example, 1, 2, 3, 4, 5, and 6. There are the 6 branches. So branches are represented with a letter B, small letter. B is used to represent branches, and here in our case we have, you can see, 6 branches. So we can just type 6 here in front of branches. In the next step, we need to define how many we have the nodes, like the alphabets, the capital alphabets that I used to represent here in this diagram. That is the point A, it is the node, and you can see this is a junction here. So these are the nodes. Nodes, as the name indicate, n, so small n is used to just represent the nodes. The counting can be done as the 1, 2, 3, and 4. You can see there are A, B, C, D. So there are the 4 nodes. So we can write in front of the nodes that there are the 4 nodes. And in the next step, we call that this is a graph. This is a graph. So what does it mean that this is a graph? It is actually a simple graph. When we just use to define arrows for the reference directions, let's suppose I used the arrows to just represent different things. And what does it mean? It means that if we need to and use the arrows, it means that we made this graph to a specific graph that is called oriented graph. So I just need OR here to represent oriented graph. An oriented graph is a specific graph which has a lot of information than just a graph. Means it contains other information, a very useful information, except only not only containing the branches and node, but also has very useful information for making and applying the Kirchhoff current and voltage laws. And the branches now become the oriented branches, but we will just use the B. Then we had discussed that there, if we connect, for example at this point, if we connect here like this is why this is called ground, and if we connect this at one point, it will become a datum node. This is not datum, DATUM, or simple R can be used here to reference. R is used to represent reference node. So this is a simple way, but discussion continue. This is what we already discussed and a lot more to recap, but I just call that it is a recap. What if we haven't discussed something like we had not discussed what is actually codes, and that is important in today's discussion. What is codes? As you can see, the codes are simple actually lines, but the codes in the sense of electrical engineering graphs means a lot. So this is an oriented graph, and if we change this oriented graph and we want to make a tree of this oriented graph, what we need to do here? There are the simple rules. We need to connect all the nodes, and the second important rule is there must not be any closed path when we are joining the points. Like here we are combining with the help of lines, we call these branches, but make sure that when we are connecting the nodes, there must be an open path, not any closed loop. Like you can see here, this is a closed path. Mean if we start from this point and we are going, and you can see if we go back to this point and reach again at the same point, that this is what we called at, this is a closed path. But there is another different technique to go to this point. Like here, if I am going to through this way and this way and this way, this is a tree, because I join A, I meet B in my way, and C and D. But there are the other possibilities. Always there are the number of possibilities in the complex system of the trees. There are more than one trees can be seen, representation of the trees, because the basic simple rule must be in your mind while making the decisions for the trees, and nothing else is so complicated that you can't understand. So I don't need to explain here a lot more things except that. Okay, coming back towards again our main focus, that is what is codes here. So first of all, let us define that this is a tree. Like these are the just nodes that we just need drawn here, and in my discussion here I used to represent that this is first point, this is the second, and there are the total three. So this is the simple, I call it as my tree. When I made a tree, you must need to check one more thing, and that is also very important, and the third and the last requirement of the tree, that is count the nodes. How many nodes are there? There nodes of the oriented graph and nodes of the tree are not changing, they are just same. As you can see, first we draw the nodes. Like you can see, when I am ready to draw the graph of the tree, I just draw the circles here, A, B, C, D, if you remember. And this is an ordinary way to draw the tree. Then after counting the nodes, like here nodes are 4, then we just subtract the 1. The formula for right that need to be satisfied here is n minus 1. Means the number of the branches here are equals to n minus 1. While here the branches are called as B, but there is no rule. There are as many branches as they are. For example, here we can see there are 6 branches, we counted. But here there is a rule. We need to focus on the nodes. Like here, if we have the nodes, number of the nodes, there are 4 nodes. So if we have 4 nodes here, so 4 minus 1 is equals to 3. So there must be 3 branches, not 4. Always 3. So this is our first branch, this is our second branch, and this is our final and the last third branch. So we satisfy all the basic properties and requirements of the tree. So this is our tree, A, B, C, D. Now what we do here, all we need to do is actually call that there are the branches, count the branch. This is first branch, second branch, and this is our final and the third branch. These are the 3 branches. And what is code? Actually codes, this is a specific word that we use here and important in today's lecture also. Codes is the branches of the graph, these branches, minus the branches of the tree. This is our tree. Okay, the branches of the graph, we simple write it here B, minus the branches of the tree. Branches of the tree can be written in the form like n minus 1. So these are actually branches. Where does this n minus 1 come from? Actually this n minus 1 is taken from the B here. This is a B. This B means that the branches of the tree. So the tree branches means n minus 1. Actually the formula of the codes is the branches of the overall network before the making of the tree means the branches of the graph minus the branch of the tree. So according to this formula, this is very important formula, need to be keep in your brains in the whole episode. Don't forget it. According to the formula, the branches are total branches before making the tree are 6. So B is equals to 6 minus n minus 1. Okay, I forget. First let us make this little bit more clear by opening the bracket of n minus 1. As you can see, there is a minus, and it has a great impact when we are ready to open this n minus 1. When this minus goes ready to multiply with n and negative 1, you can see the sign will always be changed. This is B as it is, plus n with minus n, it will be the minus n. Then this negative and this negative will become the positive, like signs when multiply. A positivity can be seen. So there is a 1, B minus n plus 1. So this is the formula of the codes that we need to be kept in our minds for the whole episode and the later on purposes of the network analysis. So if we are ready to use this very simple scheme, that codes is equals to B minus n plus 1, and this whole scenario that you are seeing here is the formula. In our case, let's see, we are ready to apply the codes formula in our case, that is, what is the total number of the branches? That are 6 branches. We have seen there are the 6 branches minus number of the nodes. 4 nodes can be seen easily here, minus 4. As you can see, 1, 2, 3 and 4 plus 1, just add 1. So this is a simple formula for the calculation of the codes of any tree. Remember that whenever we are counting the codes, there must be a tree. Without tree, we are not able to calculate the codes, because the codes come into existence after the tree. Because actually the codes are the hidden line that we just skipped when we are moving and tracing the graph and making it a tree. Like This line, you can see this line where I am my cursor right now, branch number 6, it is actually skipped and not shown in the tree. Actually there is a branch. This is what we call this is a code. This is a code. Graphical representation of the code is this. This is a code. But if we use this if we use this when we are deciding that making of a tree, we use this branch and we skip another branch like 4, then this branch that we skip here will become and treat as a code. So the specific, we can say specifically, the code is just a word, just an understanding that any line that is skipped while making a tree is taken as a code. As you can see here, 6 minus 4, the answer is definitely 2, and plus 1, the answer is 3. So 3 lines that are hidden. So in a graph of the tree, this is the first line, and you can see the first line is also missed here, another line that is skipped, and other line that is missed here, like that. So 1, 3 and 6, these are the 3 branches that are actually hidden in the graph of the tree. So this is the understanding of the codes, and we will use this formula of the code in our today's lecture because it is very, very important. You also need to keep it in your mind. So moving towards the next section, and the very important section of our episode today, that is the number of equations. Number of equations means that how many equations we need to write in for any network, for any calculation, for any system, how many equations we need to write. So first of all, very basic answer according to the mathematics rule and regulations. You heard about that. The number of the variables, look at the number of variables of any problem. For example, if we have in a problem, we also call this unknown, number of unknown also. For example, in a question, we have x and y, 2 unknowns. If we have 2 unknowns, then we will simple call that 2 equations need to be written. For example, x1 plus 2 y1 is equals to 4, x2 plus 5y2 is equals to 0, and these type of 2 equations. If we have 3 unknowns, we need to define 3 equations for solving the problem. This is a simple rule. Look at the number of the variables and the unknowns, and then write the equations. Second important step when we are ready to understand this, independent. The equations that we just write must be independent. They must not depend on the other. I will explain it what does independent mean after some time, because if I explain here, I will need to explain in the next part of this lecture. So why not I just explain once at that point. First of all, there is an other important relationship, that is voltage and the current. Voltage and current always present in every circuit. Remember that this is a very important discussion, that voltage and the current is always present. For example, any type of circuit, either it doesn't matter, we have an inductive circuit, we have either series circuit, we have either parallel circuit, either we have inductor or we have inductors, but there must be voltage and current. Both things can be seen in any network and always present in each network. For example, just for the sake of the example, we call that we have, let's suppose n nodes. Suppose that n nodes, there are the different nodes like here, 1 2 3, let's suppose, and b branches. We have b branches and n nodes, so what we will do here, if we have n nodes, b branches in any circuit, in any excited by an active, definitely they are excited by active elements, so response in a network need to be seen. What we'll do here in this type of circuit, we need to know about the branch voltages and the branch currents in any type of the circuit. There are the two things that we need to capture all time. For example, we have b branches. Suppose we call that this is first branch, this is second branch. In our case, let's suppose we have 1 2 and 3. We have 3b means 3 branches, and we need to calculate the voltage and we need to calculate the current for the all branches. Voltage and the current, both things needs to be calculated for each branch. What does it mean? It means we need to calculate two parameters. First parameter is voltage and second parameter is current for every branch. Means that we need to calculate two parameters for every branch. Like if we have here b branches, I just generalize this formula that 2b for b branches. What does it mean? I generalize the relation, means if we have b branches, we need to calculate 2b parameters. Got it? Like if I said in my case, I have 1 2 3, I have 3 branches and I need to calculate, put the value of the 3 here branches, 3 into 2 6. We need to calculate 6 parameters for 3 branches. Means the voltage and current for the first parameter, voltage and current for the second parameter, and the voltage and the current for the third parameter. So it means that we need a double parameters calculations for the each branch. Okay, then we need another important point here, that after we analyze them and after we got them, we can reduce, if we have the current, if we have the voltage, if we have the current, or two parameters actually. So if we have the voltage, if we have the current, or if we have, means to say we have one thing in a circuit, like here in this circuit, we need to calculate voltage and current across this resistor. Okay, but if I am given with the voltage, let's suppose voltage is given, then I can calculate from this parameter the current for this resistor, because I have the formulas that we discussed for the each type of resistor, capacitor and inductor. We discussed the formulas. V is equals to IR in case of the resistor, V is equals to L di over dt in case of the inductor. We have the relationship different, that is V is equals to 1 over C integral I dt. So this is a different type of the relationship that we just derived for the different capacitive, inductive and resistive networks. This can be used when we are first deriving and known one thing, because in all the formulas, calculation of the voltage can be done only if we have known quantity, like current is known. Here in each formula you can see the current is required, but if we even don't know about the current, that how we can use the formula of the voltage. One thing need to be calculated by some means, then the other one is calculated by using the formula. So this is the benefit of the formulas, that we calculate the quantities. But first thing is we need to reduce the number of the unknown. First step is we need to reduce the number of unknowns from 2b to b. Means we need to reduce the number of unknowns. Here in this a branch we have two unknowns, like voltage and current, and if we reduce by somehow to 1b, like 1B or simple B. Like if we got it, the voltage is known, current is unknown, then if we reduce it, if voltage is known and current is unknown, we means that there are no more two unknown, there is only one unknown, and that is current, and we can use the formula and calculate the current. So this is the way we call it, that we need to reduce the number of unknowns, and then the formula is valid, and enjoy the magic of the formula for the calculation of the parameters. So this is how we can calculate, and now the time is to write the equations. Okay, now we are moving toward writing the equation, but there are some again first important points that we need to describe or rewrite these points. These are very useful. So just discuss these points for using Kirchhoff laws to write the equation for the B unknowns. Like we have here, I tell you B unknowns. We have different number of equations for different unknowns. But as you know, we are discussing for just what we can say, Kirchhoff laws are really important considering the network composed of B branches. But let me show you here. The unknown quantities of the interest are the branch voltage and current, and there are the two types of the circuits, series and the parallel circuits, and we have a different type of combination seen, and you need to be kept in your mind. Okay, and we need to write B equations. First of all, this is what we understand right now. B equation for if we have B unknowns. Okay, means if we have 4 unknowns, we need to write 4 equations. And in preparation for writing these equations, the first we need to select a datum node and a reference node. For example, here if you look at this point, we need to select a datum node. Like for example, I am saying that this is our datum node. If I connect the ground level here, and this will become a reference level or the datum node. Like here I show you that this is a datum node or a reference node. So first of all, we need to understand that B equations for B unknowns, this is our first point, and in the second point we need to select a reference node. Reference node selection is really very important. Now we need to write the step number 3. What is the step number 3 here? That is the for the remaining node. Okay, first of all, let's discuss. First we need to select a datum node, and then for the remaining nodes, means like here this node is the datum node, but you can see there are the total 4 nodes, and one is dedicated for the reference purposes. Then there are 3 other, and these are called as the remaining nodes, and we need to write equations using Kirchhoff current law. We need to write the equations for them, for this node, for this node, and for this node, because Kirchhoff current law needs to be applied at the node points, and we need to write 3 equations except this one. Because this is selected as a datum node. This accomplished, it is then necessary that we write okay, for the voltages purposes. Next is that datum node is selected, and then we need to write the voltage equations. Now you know the voltage equation. For writing the voltage equation, it is applied on the loop. We need to apply loop, because we need to apply for the voltage purpose Kirchhoff voltage law, and Kirchhoff voltage law works in the loop format, while Kirchhoff current law works on the node points. And in the for the sake of the loops, we need to do here, simple, just understand how many loops and how many equations we need to write here. What is the formula for the calculation? Simple. For the point number 3, just go to the number of codes. This is a simple formula, that number of the codes. What is the formula for number of codes? As you can see here, this is the formula for the number of codes, and I star at this point also that we will use this formula. We need this formula for later on purposes, and now it is the time to use this formula, that is b is number of codes is equals to b minus n plus 1. So we will write here b plus 1. So this is a simple formula, and according to using this formula, I will explain you after a little bit. Just spend some minutes here, and I will tell you and explain you this formula according to the with the help of an example. And we can apply Kirchhoff voltage law in order that we have the total of the B equations. For example, we have the B equations here. This B is the equations. Like if we have B equations, then the answer of this will be the number of equations need to write for the KVL. Like here in our case, if we just go back, you can see here we have the B what I was saying, B is the branches layer. You can see 1, 2, 3, and total 6 branches. And if we have 6 branches, we need to apply this formula, and the answer is 3. It means we need to write 3 equations for this tree to solve by using Kirchhoff voltage law. So this is how we can apply the number of the codes formula, and the answer is the number of variables or the number of the equations, because if we get the number of unknowns or number of the variables, it is the number of the equation also that we need to write. But there is an important question, and it is the step number 4 that is very, very important, as I told you in the start also. That is the independent. What is the independent equation means here? We need to write the equations that are independent, but a set of the equation I am going to just write you for the sake of the understanding that are linearly dependent. Okay, first of all, we need to define that what is the linearly dependent and what is linearly independent. Linearly dependent means that if the set of the equation if at least one of the equation can be expressed as a linear combination of the others, then we can say this is a linear combination. Like I am going to represent here the equation, and for example, just give me a 1 minute so I can write the equation here. 3i1 plus 2i2 minus i3 is equals to 4. This is our equation number 1. Minus i1, okay, plus 5i2 plus 5i2 plus 3i3. So this is there are the 2 equations, and the answer is minus 2. So this is what we call that equation number, suppose 1, and this is our equation number 2. And if I multiply the equation number 2 with 2, let's say we multiply the equation number 2 with 2, and then like I multiply in my mind, okay, and then I add in equation number 1. Like if you see at this point, multiplying this minus 1 with 2, it will become minus 2, and then adding in equation number 1 means minus 2 plus 3 is equals to, answer is 1. So I1. Next, multiplying 5 with 2, that is 10, and then adding in 2. 10 plus 2, 12. 12i2. Then multiplying 3 with 2, 3 into 2, 6, and then adding into negative 1, that is 6 minus 1, 5. So the answer is 5i. Is equals to minus 2 multiplied by 2 minus 4 plus 4, 0. This is equation number 3. As you can see, the equation number 1 and 2, I don't know from where it comes, but they are independent and there is no relation between them. But the equation number 3 is derived by using equation number 1 and 2. So we can say that there is a set of equation, but one equation, that is in our case equation number 3, depends on the other equations, means 3 is depending on 1 and 2. So we can say the equation number 3 is linearly dependent on 1 and 2, and this equation is totally the waste and the dummy equation. We cannot use it in our purposes for solving the electrical engineering questions, especially the networking questions. This is excluded. We are not using this. We need a linearly independent equations that are not dependent on the other. Any type of the equations that are derived by using other equations are called as linearly dependent equations, and we need to exclude the possibility of those equations. So for example, let me tell you one more thing here. And for example, like if we apply the number of the codes formula to any situation, like suppose we have this type of the situation and we applied the number of codes formula to this case, and the answer, you know, if we got the answer like 3, what does it mean? We need to find out the 3 variables, 3 unknowns, and then we need to find 3 equations. And 3 equations, if we found like 3 unknowns, I1, I2 and I3, these are the 3 unknowns or 3 variables. Okay, but then the 3 equations that are necessary, I write in this sense that first I write okay, second that is fine, but the third equation I write in this way by using 1 and 2. That is not the equation that is we searching for. So by using this, if we try to find out the answer by adding or subtracting or whatever we are trying to do, by using these type of the equations, it may not be used in finding a solution. So thus we can say that these equations are the totally waste, and this set has no combinations. We need to know that the third equation may be we need to find again, and then the equations are dependent and are no unique solution may be found if we use these equations. Okay, now it is the time toward moving toward another important situation, and for this I need to again represent a very beautiful representation here. For this I am, you can see, going to use a dot, that is the D point. This is D, this is C, and this is B, and this is any other node that we call simple as A, and this is, we call it as F, and there is another node also that we are looking for, that is E. Okay, so this is a way for writing equations, and if it is connected towards the ground, we will call it as a datum node, point F, and but just count them like 1. The numbering doesn't matter if you start from here or here. 1, 2, 3, 4 and 5. Okay, the equations we write must be independent first of all, and if we are to be able to solve the equations. In addition, we desire that the set of equations to be written in terms of the smallest number of the independent variables. That is the one thing I forget to tell you in the previous section, and before writing this graph, let me tell you one thing, that if we choose the wrong answer here, for example, you can see the answer is 3 according to the number of the codes formula, and we need to find the 3 variables for applying Kirchhoff voltage law. but unfortunately we are not able to get and write the exact we get the answer 4. Then what happened? Maybe the answer we find is actually right. We write the then we need, if answer is 4, then we need to write the 4 equations. That is actually wrong. We don't need to write 4 equations. And actually if we write the more equations, what does it mean? It means that the requirement if of the smallest number of the independent choosing is clear. Like if I get the answer 4, my number of the equation will be increased. My priority should be in this sense that the set of the equations to be written in the terms of the smallest number of independent variables, that I get the minimum and the smallest number of the independent variables. And also in choosing like I1, I2 and I3, priority in this way that we have the smallest variable first and writing this variable that is in the complicated stage, writing it at the end, so that I caught easily the first I1 calculations and then the complicated and next two onward. This requirement will be clear to you after you have solved some multiple equations. We have 5 equations maybe continuously need to solve at a time. Then of course this will be looking familiar to you all. Okay, coming back toward our main point, you can see here this is independent voltage variables. You can see here, and there are the you can see a tree is shown because no closed path. Definitely this is a diagram of a tree. Right now there is a node F. As I explained that this is a datum node, there are then as many other nodes in the tree as there are tree branches. Like means that if I have 5 branches, first one, there is a formula that is the n minus 1, and if we exclude the datum node, in case of the tree we have the formula that for writing the branches, that b is equals to always less than 1 towards the node. B is equals to n minus 1. Like in our case 1 2 3 4 5 6, we have total 6 nodes. N is equals to 6. So how many we need branches we need to represent here in a tree? We definitely need 5 branches, not more than 5, because always less than the nodes. So if, as you can see, 1 2 3 4 and 5, we have 5 branches. But in a case we dedicate a node as a ground, like you can see, we call that this is a datum node. Okay, if it is a datum node, means a reference node, then it means that we subtract this the number. There is only one more node than the branches. So if we dedicate one node to this purpose, then the remaining number of the nodes is exactly equal to the number of the branches. Means right now the number of the branches is equal to the number of the nodes, because you can see here 1 2 3 4 and 5, the remaining. Now if we dedicate this, after that we can say then n is equals to b. But don't use this formula. This is just for the clarification and just understanding a basic concept that remaining the after that, after the dedication purpose, there you can see that the number of the branches are equal to the number of the node excluding this. Means there are as many as the number of branches as there are nodes. As you can see that the voltage of if we want to calculate the voltage of the node D is definitely we need to define by using the voltage source. Insert in the tree branches. We need to insert tree branches. As you can see, this is a datum node. So if we need to find the voltage of the node at point node D, or we need the voltage of node D, so we need a voltage source inserted in 3 tree branches. Actually this one branch, this branch and this branch, because the path to be chosen is this is a way to go. So this is a way. We need to choose this path. As you can see, this is a way. So this is a path towards ground. Ground is taken as a zero reference level. So that in the total, in a way, you can see there are total 3 branches that comes in the way to reach to the ground. To reach the destination, we need to go through 3 different nodes and branches. That is the 3 to 5. What we need to do here, we need to insert, I think this color is not so much suited here in our discussion, just to make it a little bit less a sophisticated diagram, I just clear this point and this point. We need to insert here a voltage source. For example, this color I just insert, this is one voltage source, another voltage source, and other voltage source. 3 voltage source are inserted in the branches, and this is a way we can calculate the voltage at the node if I insert total of the 3 voltage sources in 3 different branches. Since you can see there are no closed paths because this is a tree, so we can simply say that the current is 0, as because no open circuit have no current but voltage only, and voltage we can calculate, but current, there is no current. And the branch voltage source determine the voltage at node D. By calculating the voltages of the different branches that come into the way, we can reach to the point D, and we will say that this is the voltage of the D. By increasing the voltage sources in different and other branches also, we can find all node voltages except D1. This is the way to calculate D1. But if we want to calculate the voltage of node C, if we want to calculate the node of the voltage C, we don't need to add the voltage source of the branch 3. We only need 5 and 2. We don't need this one. And if we need to calculate the voltage of node B, you can see only one branch comes into the way to reach the ground. So only one voltage source is sufficient to explain the voltage at node B. So there are the different voltage source can be inserted into the different branches to explain different and also explaining the nodes like A and B, so we can cover all the nodes in this way simultaneously. In this equation, you can see 5 sources are sufficient to determine all 5 node voltages with respect to datum. And always remember that all the voltages are with respect to datum or with respect to ground or with respect to reference, but the most conveniently we use datum. And conversely, if the node to datum voltages are known, like this is our node, and if we have node to datum from the whole voltage is known, this is what we known. Like I said that the point D to point F means node to datum voltage is 10 volt. Then by using this node to datum voltage, 3 branch voltages can be determined. Same is the case if we know the code voltages, and we can also determine the code voltages by using node to datum voltages. No, this is node and this is the datum point F, and I said that node to datum is, let's suppose I gave you the 10 volt from node D to node F or point D to datum, there is a 10 volts. So by using this you can also find the code voltages. And what are the code voltages? Codes are those points that are actually hidden, we cannot see, but they exist. These points exist in the network all the time. We cannot see these points, but these points always exist in all networks. As here you can see these are the points, hidden points, means we can also calculate the different these points also, use the voltages of these branches, because they are just the branches like these branches, but they are just hidden. We also need these branches, means codes. We also need codes when we need to find and calculate the current. In case of the voltage, we don't need codes. Thus it seems like that the number of the independent voltage is equal to the number of the branches of the tree. Okay, like here if I say that the number of the voltage here we need in our case is 5, and it is equal to the number of the branches of the tree. We have the 5 branches because the voltage is the branch. If we need to calculate the voltage, we only need a branch, and we don't need to further define other things, because it behaves in like that. The voltage is always a branch voltage. Like if we have the voltage of the branch, this is a branch, and if we have this point, if we have this point, and like here if it is a capacitor, and there are the two node A, this is B node, this is C node, and this is capacitor, and there is a resistor. You can see this is a first branch and this is a second branch, and joining the two nodes, all the things between these, we call it simple as a branch. And the branch, we assume that the branch that you can see here, the two branches is behaves as the same as an element. Means if this element I just represent this line with a line, it is understood that in this line there is an element. If I use the word branch, it is understood that there is an element in this branch. So branch to be the same as an element, or the branch to represent a single element. One branch is used to represent a single element, and two branches are used to two elements. Like if we skip this and just replace this with the help of the sophisticated graph or oriented graph, you can see we need to represent the two nodes here, A, B and C, and two branches that are sufficient, 1 and 2. And if I just write that this is a one branch, the voltage of this will be definitely the voltage across the resistor. So if we calculate the voltage, what does it mean? We calculated the voltage across the an element. So an element can either be an active element or a passive element. Active and passive element doesn't matter in our discussion right now. What does matter here? It is the matter of the branch, that we will show you later that under some condition the two branches may be replaced by an equivalent branch for some calculations, but this will be explained in the coming lectures. Okay, now I think we need to calculate further some important points. Voltage calculation is now already highlighted how we can calculate. There are other ways. This is a one way, n-1 way to calculate the voltage, node to datum voltage in the network. There are the choices of sets of the variable from which the branch voltage can be determined, but we will make use of only node to datum voltage variables. Now n-1 is clearly, you can see n-1, I think we need to write here. n-1. n-1 means that, for example, if we have, thank God we have a diagram here. This is n. n-1 means the branch of the tree. So this is always, this is the branch of tree. But if I just write that the n-1 is always less than b, what does it mean? It means that this n-1 is the branch of the tree and this b is the branch of a graph. So the branches of the graph are always higher, means more than the branch of the tree. This is a very simple discussion, no need to explain here, because the branch, you can see there are the 6 branches. So branches of the tree are always less. There are the 3 branches only. Some branches are skipped while converting this graph into the tree. So this relation always true, that the branches of the tree or n-1 is always less than the branches of the graph. So just writing the b, it is clear that we mean the branch of the graph. By writing n-1, it is clear that we are targeting the branches of the tree. So the discussion will be continued. We will take a short break. Okay, welcome back. I just take a time to refresh my mind because I was just recording before an Urdu version, and now my mind was just held and stuck off. That was the pause break. Anyway, now I was turning to the matter of the selecting current variables fewer in numbers than the B branch currents. Means that we have the B branch again. B is the our branches, and now we are going to select the current for this B branches. And for that, what we need to do, the discussion to follow is the dual to that given for the voltage variables and begins by considering the tree of the graph. All we need to do is again look at the same graph that we discussed in the previous discussion. That was, I think, the point D and point C, like that. That is the point C. Don't compromise in writing C, by the way. And that is our point B. Here we have another point, that is our point A, and that is our point F, I think. Also we have another point, that is E. So this is very important discussion that is started from now on. This is a tree. Okay, first of all we need to do is again number them 1, 2, 3, 4 and 5. Here you can see we have 6 nodes and 5 branches. For 5 branches we need to find out the current variable especially. Here you can see the tree that I just draw. We connect a current source in place of the code of the graph. There are the codes but they are hidden. So I just need to connect a code. Here you can see there is a code, but in a tree the code is hidden. But for calculation of the current we need a closed path. The closed path only comes into being when we connect a current source and close the path by joining the 2 nodes, and that was actually a code, we call it. That is the hidden line, that is represented by dotted line, means that there is actually a line, but while making the tree we skip that, and this line is called code. And the code is now again highlighted, because if we want to measure or calculate the current we need to identify the code. For example, here we have a code and like this, and this is represents the current direction. If you look at this, it is very easy to remember right now that the current direction, and there the 1, 2 and 3, these 3 points, this one, first one, second one and third one, the current now follows this path, continues following this path and this path, like that way. Now I just need to remove this. So this is the way. The 3 branches, first branch, second branch and third branch, these 3 branches carries the equal amount of current because these are connected in series. When the branch are connected in series, the current doesn't divide but the voltage splits. What does it means? That we now place current sources to all the code positions of the graph and see that the current in each branch will be the linear combination of the current from the sources in the code positions. Like here, linear combination can be seen between for the 1, 2 and 3. And if we want to calculate the current for the other different branches, all we need to do is to add the current source in the other different code positions. Like here is also a code, and if we connect a current source here, if we connect a current source here, and if we connect a current source here also, then all what we do here, and if we connect a current source here, by doing this we can calculate the current for all the different branches. So connecting the current source in the code, if the code current is known, for example, if we connect a code source and we know the current, then we may solve algebraically for the branch currents. Hence, the number of the variable necessary to fix the 3 branch current is equal to the number of the current in the codes. What does this mean? What I am saying here, number of the variable necessary to fix the 3 branch currents, like here you can see there are the different number of the variables that are required for calculating the branch current. Like you can see here, it is a very important, and remember, listen it carefully. You can see that this point, the line number 3 or the branch 3, check that the current, the first current that is entering into the branch 3 due to this source is downward. And if you look closer, you can see there is another current source which is connected, and current is flowing in this way or maybe passing in this way, but the current is flowing downward, you can see, and again flowing through the branch 3. And now the current which is flowing through the branch C comes from another source that is connected to another code which is taken as the 2. And there may be another point, but I'm not just considering it. To make it simple, I just want to show you that you can see here the number of different currents can enter into the same line or same branch. In the branch 3, there are the 2 currents that can be seen. So line number 3 actually is it is a line that touches the 2 neighboring loops. For example, the loop that I highlighted, this one, this is a loop, closed path due to 2. There is another loop, this one. So 2 loops can be seen. If I just bold it, this is a one loop, this is one loop, and this is another loop. So 2 loops. So 2 loops can be seen and 2 different closed paths. But overall, the I that is here, the point line number 3, has 2 currents. When we need to calculate the 2 currents, so 2 variables come into exist, because there are the 2 currents of different sources are entering into the branch. Even if the 2 currents that are coming and entering into the branch from the same side, then also still we need to add up, to subtract. Means it doesn't mean that if the 2 currents are opposite to each other, one current is coming downward to the branch and the other current is going due to one source it is going toward upside, and due to one source it is going downside, we need to consider. But we always consider this situation, either the both currents are in the same side or the opposite side. But the overall discussion, you know, that the number of codes is equals to formula of the codes, if you remember, is very simple and easy to remember for me. Number of the codes formula, b minus n and plus 1. And this is the minimum number of current variables that we require. This defines the number of the current variables. According to this formula, let's suppose if we look at this side, by using this formula, number of the codes formula, you can see if we apply the number of the codes formula to this scenario, this is the tree and this is the graph, oriented graph. What we get? We get the answer 3. It means that the three different variables and three different currents are required to be calculated. So if the three unknowns, we need three, if there are three unknowns, it means that three equations needs to be derived for this type of question. And if these three equations needs to be derived, it means that the formula of the codes is sufficient for calculating for analyzing how many currents we need, for analyzing how many equations we need to derive. So how we come to know that how many equations or how many variables or how many unknowns are required, that comes to the formula of the codes. The answer of the codes formula is the minimum number of the current variables actually we require. Also note that the number is always less than b because there are always fewer codes than the branches, and we already discussed in the details and spent some time on this, that n minus 1 is always less than b because n minus 1 is the branches of the tree while the b is the branches of the graph. So this is the way. And then after we get and understand how many variables we require, then we will move toward the Kirchhoff current law or Kirchhoff voltage law. Sorry, Kirchhoff current law, because this is what we want to calculate for we are preparing this setup for analyzing and calculating the Kirchhoff current law. Not interested in right now voltage law, because current law, if we apply, then we can calculate the current. Okay, and these currents may be also in the loops form, or mesh currents, and their paths may be determined by replacing the codes upon the tree one at a time, as we did here with the bold lines. By using this, we can analyze and replace the codes of the tree one at a time. It is convenient to assign a reference direction to the loop current, which is the reference direction of the code. Means by using the reference direction of the code, like here, if you can look at this side here, if my cursor, the direction of the current can be used for finding the direction of the loop. So we always look the direction of the code or the direction of the source, current source, to define the direction of the current in the loop. Since the tree of the graph is not unique, there are many possible choices of the loop current variables, because there are possibility always that different types of the trees can be taken, different possibilities. So we cannot say that loop current variables always differ according to the position, but the answer is same. So don't be confused in this situation that what happened when this will go, what happened when this happen. Don't be mess in this type of the discussion. Okay, for the sake of an example of the identification of the independent loop currents, we are going to consider another important discussion and another very very important graph, but for this time I am going to make it a little bit open type of graph, so things are not going to be, things looks like easier to understand and easier to tell you and easier to explain. Let's suppose this is point number D, this is point number A, this is B, and this is C, and then there is another point that we call that this is point number E. All these points, if we join them, you can see there are a different combination can be seen. This is point number 1, this is point number 2, and this is point number 3, 4, 5. According to your desire, you can also write according to your setup. You are not bounded to write and choose what I am choosing. This is 6. Reference direction are given according to the current source that we connected in the code places. This is the graph. Remember, I highlight this is the oriented graph, not the tree. I'm using the oriented graph. You got it? That is the main reason. I will explain my graph also. Right now this is only the oriented graph. The point B is connected with the point D, and this is, we call it as 7, and this point C is connected to point 8, and this is what we call at 8. Is there any yeah, point C is not connected still, and it is connected with point E, and we call this as 9. Okay, now it is the time to define. First of all, I accept that you try, there are different trees are available, but just keep in your mind about the simple formula for the tree, that is you know formula for the, what is the formula of tree? Very simple, that there is no closed loop. And the second thing, that always be if they count the number of the nodes, like here you can count 1 2 3 4 5, there are the 5 nodes, so the branches should be no more than 4. Now starting with the, just select another color so that we can explain it. Like this is my first joining point, node A to node B with this color, and this is my first branch of the tree. This is my second branch of the tree. This is my third branch of the tree. This is my fourth branch of the tree. Very simple. I am taking A point as a reference because A is looking so much in the center of the hub right now, and you can see all the nodes are connected, and the other remaining are taken as the branches of the graph, of branches of the oriented graph, and these other branches are just taken as what you can say simply codes. And these are the codes that are just looking like the, actually there is a current source that is connected in these codes, but this is not shown here. Okay, means that there is always a current source in all the codes to make data is drawn to make sure they are closed. This is a closed loop, that is not written, but it is understood. You got this point? Okay, now again taking another color for the representation. What we will do here, the tree selected is identified by the pink lines. Reference direction are shown for all the branches of the graph. The paths of the graph, so paths of the loop currents are seen to include the following branches. Now we are going to include some branches. Like you can see first branch, you can see the first branch is the 1, like my cursor 1, because the direction, first of all, you can see this first one, that there is a this is the code, first code. You can see this is the first code. Got it? This is not a code, this is the branch of our tree. This is not a code, this is a branch of our tree. But the first branch, the number first branch from that is joining D to C is actually our code, because if we join the D with C, you can see there is a closed path come into being. That closed path can be seen like in this way. This is a very beautiful closed path. But if we join the D to A, this is our, these and this is our codes. Got it? This is our, these are codes. Oh sorry, I'm sorry, these are branches of the trees. But now this is our code. So this is what I am going to consider right now. This one, this case, just removing this, so it is not looking beautiful, because we also need to analyze the other loops also. So the first loop is 1, 8 and 6, and 1, 8 and 6, I will call this as a this is a one loop, and there is one current in this loop, and the direction of the current can be seen by using the direction of the code. You can see the direction of the code is upside. You got it? Upside. So this is the direction of the current according to the first loop. Got it? 186. This is a loop, and this loop has a current which I call that whatever the current, I call this loop current, that is IA, and the number of the loop is 186. For example, you can also call this as a loop 1, but I call it as a loop 186. Now looking toward another loop, that is our you can see 238. This is 238, and if we just use again the bold color, this is code, and by joining this there is a loop can be seen. Just removing this and again choosing a, this is our loop number 2, and loop number 2 name is 2, 3 and 8. The loop number 238, the current direction can be again chosen according to the reference direction of the code, that is the 2. So the direction of this is again the clockwise, but right now I am taking it as IB. Now there is another loop that we call it as 736. This is our 7. You can see this is line is 7, this is 3 and this is 6. So 736. In this 736, the 7 is the code. So 7 is considered as code, and the direction of the 7 is, you can see, is here. So this is the direction of the, that is again I'm sorry, this is the direction of the code, and we are just drawing again anti-clockwise, just removing it because it looks like so messy and chattered. So I'm just skipping this for the confusion. 736, 736, and this is taken as IC current, and then another loop that is the, you can see by the code number which one, that is 984. You got it? This 984, 984 and 984. You found it. If you not, I'm again using this one, 984. I think you got it. And the current for this one is the ID, and the last loop that we have here is the 568. This is our 5 and this is our 6, and this is our 564. Yeah, 564, 564, and we will taken it as IE. I think the time is over now. I will explain you other details in the next lecture. I will save this file here and continue the discussion from the this point. Hopefully you like this, and the next part I will continue the discussion from this point and then explain the next topic also with it. So hopefully you like it. Remember, be in your prayers and stay tuned, watch, learn, grow. This is Easy Learn.